All right, welcome back to the deep dive. Today, we're grabbing a stack of sources, specifically what looks like a really solid chapter on a foundational math concept, simultaneous equations. Our mission in this deep dive, to sort of cut through the textbook language and figure out exactly what these things are, how you actually solve them, and maybe most importantly, why they, pop up everywhere and matter.
Absolutely. And we have definitions, methods, a whole section on applications laid out right here. We want to pull out the core understanding so you can quickly get a handle on this topic. Think of it like understanding the engine, maybe, not just knowing the name of the car part.
Okay, yeah, let's dive in. The material gets straight to it, defining simultaneous equations pretty simply. It says two equations, each containing two same variables. Good examples like 3x plus 2y equals 7 and xy equals 8. Okay, but what's the big deal? You see equations with two variables all the time, right?
Right. And that's actually a crucial distinction the source makes. If you just have one equation with two variables, like 3 by 4y equals 7, the text points out there are actually an infinite number of solutions.
Infinite.
Yeah. You could plug in I plus 5, y2, that works, or x and y5.
Yeah.
That also works. And countless other pairs make the equation true.
Yeah.
Graphically, it's just a line, right? Every point on the line is a solution.
Ah, okay. But here's where it gets really interesting then. When you have simultaneous equations, two of them kind of linked together, the source highlights that suddenly the solution is unique. It gives an example, x plus 2y and y7 and 3 by 4 y equals 1. And it says there's only one pair of values, x3 and y2, that works for both equations at the same time.
Exactly.
Like two lines crossing at just one point.
That's a perfect way to visualize it. And to solve simultaneous equations, well, that just means finding that single unique pair of values. The material lays out two main algebraic ways to do this, substitution and addition or subtraction.
Okay, substitution. Looking at the examples here, it seems like you isolate one variable in one equation, like maybe you rearrange x plus 3y equals 3 to get x by itself.
Yeah, you get x in terms of y, so x is 3y.
Right. And then you literally substitute that whole 3y thing for x into the other equation, the 4 by 5y equals 29.
Exactly.
And boom, you've turned an equation with two unknowns into just one, which, you can solve.
Precisely. You've reduced the complexity. That's the key.
Ah.
Now, the addition or subtraction method, it takes a different tack. It involves playing with the equations a bit, maybe multiplying one of both.
Multiplying the whole equation.
Yeah, the whole thing by some number. The goal is to get the coefficient, that's the number in front of the variable for, say, x to be the same or maybe the opposite in both equations.
I see. So like you'd have a 4x in both.
Yeah.
Or maybe a 4x and a negative 4x.
Exactly, because then the genius part is you can just add or subtract the two entire equations.
And the x terms just cancel out.
They vanish, gone, leaving you again with a single equation, but this time just with y.
That's pretty neat.
It is. And the source notes this method is often used when you don't have to use a specific method. It suggests it can be quite efficient, if the numbers line up nicely.
So, okay, we know what they are, these two linked equations with two variables, and we've seen how you find that unique solution using these algebraic tools, substitution or addition, subtraction. But, finding x and y values isn't just a classroom puzzle, is it?
Oh, definitely not.
The source has this whole section on problems based on simultaneous equations.
Right, and this is where the power really shows up.
Yeah.
The text shows how these equations are basically the go-to tool for solving real-world problems where you have two things you don't know.
Like what kind of things?
Well, need to figure out the ages of two people based on like two facts linking them. That's simultaneous equations.
Okay.
Or trying to find the speed of a boat in still water and the speed of the river current when you only know how fast it goes upstream and downstream.
Yeah, those classic problems.
Yeah. Yep. Again, simultaneous equations. They even show setting them up for physics problems, like with distance, speed, and time for two cars moving towards each other or something.
It's pretty amazing how widely applicable this one mathematical area is. Finding abstract numbers, ages, speeds of boats, it all kind of boils down to the same process.
It really does. Identify the two unknowns, call them x and y or whatever variables you like, then translate the information you're given into those two distinct equations. Solve them.
And finding that one pair of numbers unlocks the whole problem.
That's it. Find the x, find the y, and you've got your answer.
So we've seen that simultaneous equations are, well, a powerful tool for problems with two unknowns, and finding their unique solution uses these systematic methods like substitution or addition subtraction.
Which really makes you think, doesn't it? If even these relatively simple scenarios, just two interacting variables, need this specific approach to find a single predictable outcome, what does that suggest about understanding much, much more complex systems out there in the real world? Think about economics or biology or climate, where you might have hundreds, even thousands of variables all interacting at once. How do we find those solutions?